Good day, Math 30-1s. Today we examine lesson 10.3, which is called composite functions. The essential idea today is quite strange, but a bit interesting. We are putting a function inside of another function. So the output of a function becomes the input of a different function, which is sort of strange. We'll start with investigation 1, which has two functions, a quadratic and a line, where f of x has an x squared plus x and g of x is x minus 1. And the idea again today is to put a function inside of a function. So if we have a function f of x being x squared plus x, I could take the function g of x and consider that entire y value or output an input into the function f. This would look like the function g of x going in place of every input x. So a g of x is squared plus a g of x in place of the x would look like, with its actual equation in place, an x minus 1 squared plus an x minus 1. And that could of course be simplified, but the essential point is that we are creating a new function by placing a function inside of a function. The notation for this can be a little bit tricky, as we had just learned last day about the product of functions being potentially a dot. A composition refers to taking the output of a function and making the input of a function, which will also consider this a mapping. Now the notation has a function inside of a function, but it could also look like an open circle between an f and a g. So f of g of x is not a product, filled in circle. F open circle g means the second part, the g, is what got placed into the function f. So if f starts, f is still going to start. The g that comes after is the g that gets placed in the middle, and there won't always be f's and g's. So we'll see this notation as we move through today's lesson, but I'll give you a bit of a quick idea of where this can be used in a very applicable sense. If people were to convert units, we could actually change an equation to deal with different units. So I came up with a fairly logical example, but a bit strange. Imagine a person with 3 hours of time to walk from a reference point. You have 3 hours of time. Their location, d kilometers, is based on how fast they travel in k kilometers per hour. So their distance is based on their speed in kilometers per hour at 3k plus 4. An American scientist laughs at the strange Canadian units of kilometers per hour and knows that kilometers per hour is created from miles per hour with the equation kilometers per hour could be created by multiplying 1.6 times the number of miles, where k is kilometers per hour and m is miles per hour. So really we have one equation which tells us a person's distance based on a speed in kilometers per hour, and a second equation which relates kilometers per hour to miles per hour. Again, kind of strange. But an expression for the person's location based on speed in miles per hour, starting with a speed in kilometers per hour, could be. Now I'm going to take the person's distance based on their speed in kilometers per hour, and when I see k is equal to 1.6 m, I can replace that k into this k because they both represent kilometers per hour. So I'm going to swap out that k with the function 1.6m. And in place of k, I am inputting 1.6m. And now we end up with an equation for the distance based on the speed in miles per hour as a 4.8 m plus 4. What results is an equation for a person's distance based on their speed in miles per hour. This type of logic only comes with quite a lot of practice, but compositions of functions can have a deep-rooted implication in terms of something as simple as converting units. So let's go on and look at the simplicity and the standard types of questions that we can come across to build this concept. In Investigation 2 in the next page, we have a composition, also known as a mapping, with very specific inputs. So we have an f of x, a line, a g of x, a line, and an h of x as a quadratic. We have 3 separate questions, all ask us to determine f of g of 3, which means we're looking very specifically at an answer to the question as a value, g of h of negative 2, and an h of 2. And the last one seems a bit strange because we're placing a function inside of itself. Well, let's do this one step at a time, and for letter A, we have f of g of 3. First thing we need to do is examine what is the very input asking us. Well, we have a g of 3. That means we're taking the x value of 3 and plugging it into g. Let's go up to the function g and plug 3 in. G of 3 is 3 plus 6, which means a 9 would come out. I am replacing g of 3 with a 9. That output of the function g is now becoming an input into the function f. In the brackets is our input. So now this output has become an input into the function f. So let's go to the function f, plug in a 9, and see the result. F of 9 is 4 times 9, 36. So the input of 3 becomes the output 9, which becomes the input into f, becomes the output 36. Sounds a bit tricky, but this makes a lot of sense with only a little bit of practice. Feel free to pause the video and attempt B and or C, though I will keep going. In this notation, g of f of negative 2 means we want to start with the g and rewrite this perhaps as an h of negative 2 so that we don't make any small mistakes. And we can plug negative 2 into the function h, and a negative 2 squared produces a positive 4. And so the output positive 4 replaces the h of negative 2, which becomes the input 4 into the function g. 4 plus 6 gives us our final answer of 10. And lastly, we have h of 2. And if we plug 2 into the function h, 2 squared is a 4. 4 comes out, which becomes the input, which goes back into the function h. 4 squared is 16. So I've been talking quite a bit about inputs and outputs, and there's a way to map this using something called an arrow diagram. Just to reiterate this idea of inputs becoming outputs, we're going to map this with an arrow diagram. So question asks for a function f and a function g, determine f of g of 2. So what we're actually doing is we're starting with an x value. We are plugging it into a g function and determining g of, in this case, it'll be 2. So we have a g of 2 output. This output is going to become an input into the function f, and the input becomes a new output into our function f of x, which is again our final answer. So when a 2 value for x goes into the function g, 2 minus 1, 1 comes out. This is our output. Technically, though, it becomes an input into the function f, and a 1 goes in. 1 squared plus 1 is a 1 plus 1. A 2 comes out as our final answer. Now this is coincidental that it matches and is a bit of a palindrome, but is a 2, 1, and a 2. So we can map them together and gives us a bit of a visualization. Another way that we can represent functions in math is using ordered pairs. Input, output. Now in this case, no equation is given, which implies that for the function f, this is all that exists. Your domain is 0, 1, 2, 3, 4. There is no 5, there is no negative 1. This is your function. For g of x, we have a very specific list of 1, 2, 3, 4, 5, 6 ordered pairs. This is the entirety of the function. So 1 question together and 5 you might try. Question asks us to determine f of g of 1. First thing to determine is, what is g of 1? What is g of 1? Looking at the function g, it gives us some very specific inputs, and we're focusing in on the g value input of 1. What comes out? 0. That output becomes our input for f, so then we go to our function f, which lists based on an input of 0, an output of 0. F of 0 is 0. Feel free to pause the video and try 5 more to see if there is an answer and what it might be. F of g of 2. G of 2 is where we start. Plug 2 into the function g, 1 comes out. F of 1, input of 1, 2 comes out. Final answer, 2. 2-letter I. G of f of 2, starting with the function f, plug in a 2, 5 comes out. Then we go to our function g, ask when 5 goes in, what comes out? 4 comes out. Final answer is 4. F of g of 3, starting with the function g, plug in a 3, 2 comes out. F of 2, 5 comes out. G of 1, starting with the function g, plug in a 1, 0 comes out. What is g of 0? Negative 1 comes out. And lastly, g of f of 4. What is f of 4? Plug in a 4, 20 comes out, and then determine g of 20. I don't see an input of 20. This implies there is no solution. Ordered pairs can be a little bit tricky, but with a little bit of practice, they can become quite simple. So we're going to go back to equations for the moment and talk a little bit about simplifying them. So to start, I've got a very specific input, and then we'll talk a little bit more broadly about simplifying an equation as a general statement. In example 2, we've got a radical function and then a quadratic. I'm asking us specifically to determine g of f of 0. First, what is f of 0? Plug a 0 into f. 0 minus 1 is the square root of negative 1, which doesn't exist. So if I can't get an output for f of 0, I can't compute g of something. So there is clearly no solution to this question. There is an issue with the domain that I chose. Look though what happens if we were to not be specific and ask generally, what is g of f of x? G of f of x means we're going to plug the function f into g. I'm going to rewrite the function g, which is x squared, but in place of the function g, x squared, I'm going to write the entire function f in the function g. So I write square root of x minus 1. Most people would notice that there's a square root and a square, and they would cancel out, and the function simplifies to be x minus 1. At this point, I might say, hey, what if I were to ask, plug a 0 in? 0 minus 1 is negative 1. There's a solution. But a moment ago I said, when you plug in a 0, there is no solution. The one thing we must remember is that even though functions might be manipulated or changed through a composition, the initial domain is still very, very important. The initial domain said x has to be greater than or equal to 1, and that must stick. X has to be greater than or equal to 1. So even though in its current form anything could get plugged into x, the original domain is still implicit in the question. As we move on to example 3, we've got some more complex equations like a logarithmic function, a quadratic, and a line, and I've asked for x's, which means general equations, to be created. These may take a little bit of time, but it goes quite quickly if you get a little bit of practice. For the first one, f of g of x is asking us to rewrite the overall structure f with g in it. The function f is an x plus 1. So I'm going to write in place of every x a bracket. It is good to get in the habit of this. So the overall structure for f is x plus 1. In place of that x, I'm going to rewrite the function g inside of it, which is x squared plus x minus 6. We can tidy this up a bit and combine like terms to say x squared plus x minus 5 as a final answer. There are no restrictions other than in the log function, so we don't need to write any restrictions. For letter B, the g of f of x means that in the function g, x squared plus x minus 6, I can put the function f in there. X plus 1 squared plus x plus 1 minus 6. This could be tidied to an x squared plus 2x plus 1 plus x plus 1 minus 6 into an x squared plus 3x. There's a 1 and a 1 makes a 2. 2 minus 4, 2 minus 6 makes a negative 4. And there is g of f of x. F of x is the function f going into itself. And so we have x plus 1, but in place of the x, we're putting the entire function x plus 1 into the x, which results in an x plus 2. Again, sort of strange, but with a bit of practice makes sense. G of x into g of x can be slightly more exhaustive. So we have a g of x. So I'm going to rewrite g of x as x squared plus x minus 6. And in place of every input, I write x squared plus x minus 6. X squared plus x minus 6. And just because of time, I'm not going to expand the trinomial times itself and tidy up our like terms. But that is the idea behind a composition of a quadratic within a quadratic. And the last one, h of f of x, has a log base 2 of x, where x is actually f of x, x plus 1. Now we don't have to write a restriction on x plus 1 because there is no restriction for x plus 1, and the restriction is already implicit in the function as it is. You're not allowed to have a negative or 0 input. It doesn't need to be stated because we can still see that. So logarithmic, sinusoidal, rational, exponential, polynomials, they're all a part of this unit. Now the last couple questions get us to think a little bit more strangely. The question below asks us to determine an original function from a composition. So if the function h is created from g going into f, what is a possible f of x and g of x? When most people look at letter A, they see this repeated x minus 2. Imagine that instead of an x minus 2, you are leaving these blanks. And in place of those blanks were x's. X squared plus x plus 1. The overall structure of these inputs is the outside function f of x. And what was placed into these inputs? The function g of x. And g of x is the function x minus 2 that was placed inside. Being able to notice what could the original functions have been is a little bit of a trickier one that again gets simpler with practice. For letter B, we've got a couple options. We have h of x is the square root of x minus 1 cubed. A few people might notice options, and they might say, well, the square root of x could be your overall structure f of x, and what got placed into there was x minus 1 cubed. That could be a possible answer. Other people might say, well, what if x minus 1 was your input into the square root of x cubed? The square root of x cubed could be your original function, and maybe a simpler x minus 1 were plugged in. In this case, there are multiple options, and there are multiple more, but there is not one answer to this question. And lastly, at the very bottom, we have a couple statements. F of 3 is 5, g of 2 is 3, and so on. And the question is, determine h of f of g of k of 0. It sounds like this is going to be an exhaustive question, but it actually works out to be perfectly stated. Rewriting this in its more helpful form, we can say h of f of g of k of 0. And we'll work our brackets back out. And we start in the middle and ask ourselves, what is k of 0? Now, conveniently we don't have an equation or a graph or an ordered pair or a mapping, but we have the one piece of information we need. What is k of 0? 2. We can rewrite this, but instead of k of 0, I'm going to write a 2. What is g of 2? Conveniently, g of 2 is 3. So instead of g of 2, I will write a 3. F of 3. Again, quite conveniently, we are left with a perfect fact. F of 3 is 5. F of 3 gets replaced with a 5. And hopefully we know what h of 5 is, and in fact h of 5 is a 9. And what turned out to be a quite simple question looked fairly complex. Today we are examining composite functions, the idea of putting a function inside of another function, and the most important part is getting comfortable with the notation so that it feels less strange. Good luck.